Okay, so the glow discharges are the stable discharges. So including subnormal glow, normal glow, and abnormal glow. And in glow discharges, between cathode and anode, we can see several luminous zones. So later on, I will explain the reasons for different luminous zones for glow discharge. Okay. And if we keep increasing current, we might get a discharge with the arc form. And there are different arcs. So hot fermionic cathode or cold cathode. So there are different arcs. Okay. So arc is characterized with high current density and low voltage arc in this region. High current density, but low voltage is discharge. Okay. And in the left figure is a hot fermionic arc. So the bottom side is cathode, and the top side is an anode. Okay. So in this type of the arc, the cathode is at high temperature, very high temperature. So for conducting materials, if you heat it up to high temperature and then apply a negative voltage to the hot cathode, the electron can emit out. That is named fermionic emission from hot cathode. Okay. Fermionic emission of electrons from hot cathode. Okay. Because the electron can overcome the work function by just applying a small electrical field. So the electron will come out from the surface of a hot conductor surface, okay? So this example is a carbon arc in air, okay? And in this figure, we have a small cathode, and large anode. And for this kind of hot fermionic arc, it will form diffusive arc. This arc is called also known as the diffusive. Diffusive arc, because if we see the surface of anode, almost the most part of the surface is covered by the plasma, by arc plasma. So the arc plasma in this case is not localized. Okay. And the other important type of the plasma is the cold cathode plasma. So if you use a cathode at low temperature and then generate a plasma with high current density, you will get a cold cathode plasma. So in a cold cathode plasma, the plasma just look like the flash or the lightning. Between the cathode and anode. So it's cold cathode arc. cold cathode arc. So for a cold cathode arc, since their discharge is usually localized at small spots, so that the current density is very high. And the spots will not at a fixed position, but it will rather wrangling around. So usually if you have an arc in your plasma system, you will see the trace of the arc forming on the cathode surface and on the anode surface. Okay, so this is the trace of the spots of a cold cathode arc. And this picture is taken from the surface of cathode, and it's named cathode erosion. And there are also other types of arc: high pressure arc, very high pressure arc, and low pressure arc. Okay. Okay, and in this slide, we come back to the glow discharge. So including subnormal glow, normal glow, and abnormal glow, right? There are several luminous zones between cathode and anode. Between the cathode and anode, so this figure shows the luminous zones in a discharge tube. And the title is the architecture of the discharge. So again, here is a quartz tube, and the left end is cathode, and the right end is anode. And you can fill in the quartz tube with a gas. For example, you can fill in the quartz tube with argon, and control the pressure of argon gas to a certain range. Usually it's around a few hundred millitorr to a little bit less than 1 torr. Okay? And then apply a voltage between cathode and anode, and then generate plasma. So once you generate plasma, the quartz tube will show several luminous zones. Okay. So this region is called positive column. So this is one luminous zone. So in this region, we can see a light coming out. Okay. And on the anode surface, there is also a thin layer of glow region, and this region is called anode glow. On the surface of it, very close to the surface of anode. Okay, and then on the left side, this part, the cathode region, right? So on the surface of cathode, near the surface of cathode, here is a thin layer of cathode layer, thin layer of glow, which is named cathode layer. And this region is negative glow. So actually there are several regions from cathode to the anode. We can see the cathode layer, negative glow, positive column, and anode glow. Several glow regions. And the other space between these glow regions is named dark space. So there are also several dark spaces in the discharge tube. So on the cathode surface, there is an external dark space. And between cathode layer and the negative glow, here is a cathode dark space. And then between negative glow and positive column, here is the Faraday dark space. And this place between positive column and anode glow is anode dark space. Okay, so there are several regions of luminous zones and several dark spaces. Dark spaces, okay. And the figure B shows the luminous intensity, right, related to the figure A, to figure A. Okay. So here is the positive column, and here the anode surface, right, and negative glow, and then this part is the cathode layer. So the vertical axis is the luminous intensity, the light intensity, right, and the horizontal axis is the position in the discharge tube, right, and the left end is the cathode surface, right end is anode surface, okay, and the intensity has a dip here, right, between positive current and anode glow. So this dip here has the lower intensity compared to positive current and anode glow. And this is related to anode dark space. And in this region, between negative glow and positive current, the luminous intensity is also lower. So it's named the Faraday dark space. And in this region, right, between negative glow and the cathode layer, here, the intensity of light is almost zero. And this part is the real dark space, okay, is related to this region, cathode dark space, okay. And then figure C is the potential distribution across this quartz tube, across the discharge tube. So the left end is the cathode surface. So the cathode surface has lowest potential. And the right end is the anode surface. So if we have a small anode, the potential of the anode will be higher than the potential inside the plasma. But if we have the same area of cathode and the anode, the potential of anode should be less than the potential inside the positive column. Okay. So this is for the small anode. And if this is a large anode, the potential distribution should form a dip like this way. Right. So this is for a large anode, and this is for small anode. Small anode. And we have already known this phenomena because the space charge change from positive space charge to negative space charge. If we shrink the area of the anode, okay. And this figure is important here because we can see in a positive current, the potential, right, inside the plasma, inside positive current is almost the same. There's only a very small potential difference. So if we divided potential by the distance, we can get electrical field. So it means inside positive current, the electrical field is very small. Okay, so most potential drop exists near cathode surface. And if we compare the potential profile with the architecture of the glow discharge, we can see the potential drop actually exists in this region between cathode surface and the edge of negative glow. Edge of the negative glow. And this part includes the cathode layer, acetone dark space, and cathode dark space. Cathode dark space, okay, this region. Most potential drop exists in this region. Okay, this is very, very important part for glow discharge or DC glow discharge. Okay, and length of this region is marked as D sub C. D is the distance. C is cathode. Cathode. Okay, so this is the cathode layer thickness. Cathode layer thickness, and the potential drop here is V sub C, cathode 4. So here is the cathode 4 and the cathode layer thickness. And cathode layer thickness, D sub C, right? Cathode layer thickness, and V sub C, cathode 4. So if you apply 600 volts of DC bias, right, between cathode and anode, you will find out most potential difference exists in this place. So in the cathode layer thickness in this region, the potential drop is a little bit higher than 600 volt. Little bit higher than 600 volt because you need to add the applied voltage and plasma potential. Right. So the cathode 4, the value of the cathode 4. Right, for general diode system, cathode 4, right, equals to the applied voltage plasma added plasma potential. Applied voltage and plasma potential. Okay, so if you apply 600 volts of DC bias, you might get 620 or 660 volts of cathode 4 or cathode drop, cathode 4 or cathode drop, okay, in this region, okay. And there is almost no potential difference or very small potential difference inside the positive current. So that the plasma behavior in positive current and in the cathode 4 in the cathode zone region are different. They are different because the electrical field are different and the collisional process are different. So their behaviors are different. Okay. And there are other things there. The density of charged particles, okay, and the current. Okay. So the important part are the first 4 figures or first 3 figures, and the top figure is the architecture of discharge, and then the distribution of luminous intensity, the distribution of potential or potential profile, and the electrical field. Okay. So next slide, Next slide describe the cathode zones and the positive column and the anode region. So you can read the details of the description in Chapman's book, The Glow Discharge Processes, the Chapman's book. Okay. So here, right, in the cathode zone region, right, from cathode surface to the edge of negative glow, right, the cathode zone region, right, large potential drop exists here, and this potential drop is named cathode 4, and its nomination is the V sub C, and the length of this cathode zone region is called cathode layer thickness, and it's written as a D sub C. Okay, you can check it with the figures in a previous slide. Okay, and here is another important thing. So we can generate a plasma without a positive column, but we need the cathode region, cathode zone region, to generate plasma. So if we come back to the previous slide, okay, if you have a system, a quartz tube, you can make experiments. So if you can move the anode, okay, so you can push the anode toward the cathode. So with fixed working pressure, for example, if you fill in argon, you can control the argon pressure at around 0.1 torr or 100 millitorr, and then generate your plasma by the DC power supply. Okay, and at the beginning you might see a different luminous zone, and later on, if you can change the position of your anode, you can push it toward the cathode, this direction. So if we push the anode to this place, you can see the length of positive column decrease, but the cathode zone region is not affected. They will remain as the same dimension. So we can push the anode again to this place. Push it to this place. And then positive column disappear. But you still can have negative glow. Okay, so you can actually push it not all the way near this place, the edge of negative glow. But if you push the anode further, the plasma will disappear. Okay, so the cathode zone is important for the generation of plasma, and positive column is not necessary exist in your glow discharge system. Okay, so you can run this kind of experiment. And if the anode position is fixed, right, usually it's difficult to move the anode in a vacuum system unless you have a special design, right? So if the distance between cathode and anode is fixed, you can also run the experiment, another kind of experiment. So you can change pressure you can change pressure. So for example, at the beginning, you might generate plasma with argon pressure of 100 millitorr or 0.1 torr, 0.1 torr. And then you can start decrease the gas pressure. So from 0.1 torr, right, 0.1 torr equal to 100 millitorr. You can start decrease. So for example, 0.05 torr. So it's around 50 millitorr. So what will happen if you decrease the pressure in your discharge tube? What will happen? Okay. So for DC discharge, right, in the Paging's curve, the horizontal axis is P times D, PD. Okay, so we can consider a PD as a variable. Okay. So for example, in this place, the PD is about 1 or 2 centimeter tall. 1 or 2 centimeter tall. Okay, so if you decrease pressure, but the PD minimum is still with the same value. So if you decrease pressure, you need to increase the distance, right, for this value, D. But the D value here is actually the cathode layer thickness. So actually, D is cathode layer thickness. The D is not the distance between cathode and anode. So cathode layer, actually D is the cathode layer thickness. So again, in this figure, if you decrease pressure from 100 millitorr to 50 millitorr, the cathode layer thickness will increase. Cathode layer thickness. So it means this region will increase. So that the negative glow, right? So in this figure, the cathode layer thickness is in this region. So if you drop it, right, from 100 millitorr to 50 millitorr, the cathode layer thickness will move to this place, and the negative glow in this place. And if you keep decreasing, you can find out the cathode zone will expand, decreasing after you decrease the pressure. The cathode zone will be extend, so maybe the negative glow will fall in this region. So if you can decrease your pressure and still let the plasma keep running. So eventually you can get a plasma with negative glow in this region. So maybe you keep dropping to a 0.01 torr, right, or 10 millitorr. Or it will increase 5 times or even smaller pressure. So eventually the positive current disappears and the cathode layer thickness increase. So you can run this kinds of experiment and find out what happened. So the the positive current is not necessary, right? So you can generate a plasma without a positive current, but you always need the cathode zone, cathode region, right, from cathode surface, and then the cathode dark space, and then to the edge of negative glow. You need this region to keep plasma running. Okay. And here is the physics or the reactions or physics in the cathode zone. So from the dark space here, acetone dark space, the first part is the acetone dark space. Okay, so here are several luminous zones, and luminous or the light emitting, right, is originated from recombination of electron and positive ion, or the excitation of radicals. And if we are just focused on the recombination process, the recombination process means an electron meet a cation. They will recombine so that the charge disappear, change to a neutral species, right? And then accompanied with light. So this is the recombination process. And this process will cause luminous, because on the left side, right, a free electron and a cation, right, the energy of these two species is higher than just a single neutral atom. So on the right side, you need to add the difference of the energy. And the difference of energy is released by light emission. So this part calls the luminous. Okay. So from the left side of this discharge tube, the surface, here is the surface of cathode. So when you generate plasma, there are cations and electrons. Cation will collide with the surface of cathode, cation, because of the potential difference, right, in the cathode layer. So cation will collide with surface of cathode, and then knock out electrons. And this is caused by the gamma factor. Gamma. Secondary electron. Right, by the gamma factor. So when cation collide with the surface of cathode, they can knock out electrons from cathode surface. And these electrons at the beginning will accumulate on the surface of the cathode. And then the electrons can experience the electrical field here, right? So that the electrical field will pull the electron out from the surface of cathode. The electrical field, right? The electrical field is pointing toward the right direction, but for the electrons, they can be accelerated and pulled out along the right direction. So electrons start escape from surface of the cathode, and in the meantime, the energy of electron will increase. And then when this electron meet cation, they recombine. And then recombination will emit light. They recombine, follow this equation, recombination. And this causes the luminous in this region, cathode layer. Okay. This is the first luminous region caused by the recombination of electrons coming out from cathode surface and the ions coming from the plasma and then traveling toward the cathode surface. So they meet at this place and cause recombination and luminous. And this luminous is cathode layers. Okay. And then electron keep traveling because of the electrical field. So when the electron traveling across the cathode layer in this region, across this region or cathode layer thickness, this region, they gain energy, right? They keep gaining energy by electrical field. In this region, because of the potential difference and the electrical field here. So when electrons travel across this region, they gain energy. But electron needs high energy, higher than ionization energy of gas species to undergo electron impact ionization. Okay, so when electrons travel to this region near the edge of negative glow, the energy of electrons are high enough, higher than ionization energy of gas atom. So in this region, so at the beginning, when the electron escape from the cathode surface, their energy are very low. But after they travel across this region, they get a very high energy. So the electrons become primary electron, high energy primary electron. So when electrons collide with neutral gas atom, they can ionize the gas and generate electron and ion pair. And this process happened in negative glow. Negative glow. So negative glow is very important in a plasma generation. Okay. So the most important reaction happen here. Electron impact ionization, and the electron here is primary electron with very high energy. So the energy of the electron is obtained from electrical field in the cathode layer. Okay. And then after electron collide with gases, their energy become smaller and smaller. So the energy of the electrons is smaller than the ionization of gas atoms. So even when electrons collide with these electrons collide with gas atoms, they cannot ionize. The gas atom. So the electron, after they travel across negative glow, they lost energy, and then come to this region, So in this region, there is no enough electron impact ionization because the energy of the electron in this region is very small after the collisional process. Okay? Okay. And since the left side is cathode, the right side is anode. Right side is anode. So actually, there is a small potential difference, in this place. So the electron, when they travel across the Faraday dark space, across this dark space, they can be accelerated by a very small electrical field. Very small electrical field. So that the energy of the electrons, the average energy of electrons might achieve 1 or 2 electron volts. 1 or 2 electron volts in this region. And then remember this curve? Electron energy distribution function, F of sub E. So in this region, this low energy electron might gain energy from a very small electrical field. And the average electron temperature or electron energy might reach 1 or 2 electron volts. For example, here is a 2 electron volt, right? So the average energy of the electron reaches 2 electron volts. But if we look at the high energy region, the energy of electron might be 16 electron volt, and this part is the high energy tail. So after the electrons travel across Faraday dark space, the average electron energy is 1 or 2 electron volt, or even a little bit higher. But small amount of the electron has very high energy. And this part of a high energy tail, this electron cause the ionization process in positive column. Okay. So even though the electron energy is, average electron energy is much less than the ionization energy of the gas atom, you can still get plasma because of the high energy tail. So the glow, after some electrons ionize the gas or excited the gas, and then the gas come back to the ground state, or recombine with the electron, they emit light. Okay, so this is reactions in positive column. Okay, so the reactions in the cathode zone and in positive column are different. So in the cathode zone, the discharge process is caused by high energy electron, primary electron, right? And in the positive column, the ionization process is caused by the high energy tail of the electrons. But the average energy of the electron is much less than ionization energy of gas atom. Okay. So the difference make the characteristic of negative glow and the positive column, different. Okay, so these paragraphs describe these reactions I just mentioned. Okay, the dark space and Kessel glow region. Okay. And here are three tables for the gross discharge. The setup is the same as the previous slides. Okay. So in this table, the first table, we can see here's the normal KSO4. The normal KSO4. Okay. KSO4 has the potential drop in the KSO region, in the KSO layer region. So this row shows different gases, and this column shows the KSO material. So you can find out the normal KSO4 for your system. So for example, if you generate argon plasma, so here is the argon plasma. And if you use gold or silver as the KSO material, the normal KSO4 is around 130 volts. Okay, for the argon plasma. And if you use air as the working gas to generate plasma, and use silver and gold as your KSO material, the KSO4 is around 280 volts. 280 volts. Okay, and if you compare the KSO4 with different materials, different KSO material, you can find out, for example, here if you use potassium as your KSO, the KSO4 is small, much smaller than other KSO material. Okay, the reason for the difference of the KSO4 with the same working gas is the gamma factor. So this part is the gamma factor. Gamma factor, right? Gamma factor will influence the capability of electron emission from KSO surface. So if the gamma factor is larger, you can generate more electrons by ion bombardment, by cation bombardment, right? So you don't need a very high voltage to generate plasma. Okay, and from this table we can see potassium and there are maybe other potassium. Okay, you cannot see much difference. Okay. Potassium or maybe sodium. Okay. If you use potassium or sodium to generate plasma as a KSO to generate plasma, the KSO4 is only 100, 200 or less, or 200 or less, and for argon plasma, and for this row there are different gases. So for the different gases, they have different ionization energy. So this part is related to the alpha factor or epsilon factor in the tungsten analysis. Okay, so this table shows us the effect of KSO material and effect of the gas to the discharge. Okay. Okay, any question?